So our last unit of the year, we're really only going to do half of it, just to kind of get some of the basics down and the different rules that honestly you probably would see used a little bit more. Okay? So today we're just going to talk about basic probability, what probability is, a couple of really important vocabulary terms that we'll use throughout the next couple of lessons. So I already wrote a couple things down and I'll add to that just kind of as we talk about it. So I'm sure you guys know what probability is. The general idea is just the chance that something will happen, right? The probability that it's going to rain is 20%, whatever. So probability can be expressed as a percent, as a decimal, or as a fraction. Personally, I don't really care. Excuse me. How you express it. We'll talk about rounding in different scenarios. I just want to make sure you understand your assessment is most likely going to be mostly multiple choice. So understanding how to identify each way to write it. And then kind of the notation that we will use for probability will look like that. So P of A. So it kind of looks like a function. And that A is the outcome you want. Okay, so a probability experiment is just an experiment that has multiple outcomes. And then an outcome, all outcomes are just all different versions of the possibilities that you could create. And then the complement of an event is the probability of the opposite of an event. So if there is a 30% chance that it is going to rain, the complement of that would be that there's a 70% chance that it's not going to rain. So both of these should always add to 1. The notation for complement is P of A, and then that A always has a bar on top of it. And so again, the probability of your event and the probability of its complement should always come out to be 100%. And that's the maximum probability. You will never have a probability that's more than 100%. So the big idea for today is the difference between theoretical probability and experimental probability. So theoretical probability is what should happen. Okay, so for example, I got this 6-sided number cube here. So there is not one number that appears more than another. All sides are equally represented. So in theory, the probability that I roll a 5 should be 1/6. The probability that I roll a 4 would be 1/6. The probability that I roll an even would be 3/6 or 1/2. And so the theoretical probability is what should happen. Okay, and so the way that we always calculate that probability is the number of favorable outcomes. So what you want, so for example, if I want to roll an even, I would have 3 favorable outcomes over the total number of outcomes. So there's 6 total outcomes. Okay, so the experimental probability then is what actually happens in your experiment. Okay, and so in class, I usually do an activity to open up this lesson, and we actually do an experiment, which is, in this context, not going to do it. So if I rolled this dice 36 times, according to the theoretical probability, I should roll a 1 6 times, a 2 6 times, 3, 4, 5, and 6 all 6 times, because there's a 1 in 6 chance for each number, so I should get each number 6 times. But if I were to sit here and roll this dice, oh my gosh, I skipped, I went 1, 2, 3, 4. This is my son's counting dice, by the way. And so if I were to actually roll this dice 36 times and record each number, most likely I'm not going to roll a 1, 2, 3, 4, 5, and 6 times each. I might roll a 6 10 times and a 2 only 3 times. That is your experimental probability. And so the way we calculate that, the overall idea is the same, except we would now just take the number of successes over the number of trials. Okay, so it's again the same idea in terms of how you figure that out, but what we're looking at is different. Okay, so if we look at these examples, just calculating basic probability, for maybe the first two, I'll show you how to express it in all 3 different ways. And then again, from there, unless the directions specifically tell you how to express it, you should express it how you can picture it, which for most people is going to be a percent. And I'll explain what I mean by that kind of as we're going through, like especially when we get to number 2. All right, and so this one says find the probability of randomly selecting the following in one draw from a jar containing 8 blue marbles, 5 red marbles, and 2 orange marbles. So classic probability problem. Every probability loves marbles. All right, and so first of all, there's 13, 14, 15 marbles. So that's going to be in the denominator of all 3 of these. And so the probability of orange would be 2 over 15. Okay? All right, and so that would be how we would express that as a fraction. You always want to make sure those fractions are simplified, which in this case it is. So then if we wanted to express that as a decimal, I would probably put 13 or I was going to a percent. So I'd probably do 0.13. Now a percent, you need to make sure you round your percentages at least to the 10th spot. So if you're going to write it as a percent, you want to make sure you move your decimal over and then round it. So if we multiply that by 100, that would be about 13.3%. Okay. The reason I always ask to move the decimal before you round it is because we want to make sure our probability is as accurate as possible. And so if we were to just put 13%, if you were to round your percent to just 13%, well, 12.5 technically rounds to 13, and 13.4 also technically rounds to 13. So when you round to the nearest whole number, this is almost a full percent different, which doesn't seem like a lot because it's just 1%, but depending on what you're talking about, that 1% could be a really big deal. And so you always want to make sure your probability again is expressed as accurately as you can make it. And so you never want to round your percent to a whole. Always round it to at least the tenths. Okay. All right, so next we're going to find the probability of a blue marble. And so there are 8 blue marbles, still out of 15. So if you left it as a fraction, you'd be done here. 8 out of 15. I'm going to skip the decimal. Honestly, like I said, most people will choose to do percents here. And so that would be about 53.3%. Okay. And then the last one would be the red marble. So the probability of red would be 5 out of 15, which would simplify to 1/3, which is 33.3%. Okay, so what I said before, when you're expressing probability, what I honestly care most about is that you can kind of visualize what that probability is. So if you can think of like a pie chart and understand that 8 out of 15 is going to be close to 1/2, then leave it as a fraction. But if you can't like visualize what that fraction is, just do a quick change to percent. Because I want you to make sure you understand like that you can visualize what that probability is going to be. So when you're looking at like 1/4, 1/3, 2/3, 3/4, most people can very easily picture that in like a pie chart like that. So that I'd say leave it as a fraction. But if you like for this one, if you can't like picture what that would be, I can picture 13.3% better than I can 2/15. Okay, that's kind of what's important to me. All right, and so this next one says each section of the spinner has the same area, right? So the spinner was spun 20 times, so that's our experiment right here. The table shows the results. For which color is the experimental probability the same as the theoretical probability? Okay, so this goes back up to here. So again, theoretical probability is what should happen. So the theoretical probability, if this spinner was separated into 4 equal parts, in theory, you have a 1 in 4 chance of landing on red, a 1 in 4 chance of green, blue, and yellow. Okay, but as you can see here, when we did the actual experiment, we did not land on the 4 colors the same number of times. So the experimental probability is different from the theoretical probability for most of these colors. So in terms of the experimental probability, if it was spun 20 times, we spun red 5 out of the 20, green 9 out of the 20, and then blue and yellow 3 out of the 20. So in terms of which one ended up being the same as the theoretical probability, that would be the red. Because if you take 5 out of 20 and simplify it, that would be 1/4. So our red marble ended up having the same experimental probability. Okay, all right, so now we're going to look at this just in a different context. So we looked kind of at a table, now we'll look at a graph. So in the United States, a survey of 2,184 adults ages 18 and over found that 1,328 of them have at least one pet. These types of adults, or the types of pets these adults have, are shown in the figure. What is the probability that a pet-owning adult chosen at random has a dog? So if we think of favorable over total, there are 916 that have a dog, and if we're only focusing on pet-owning adults, that denominator is going to be 1,328. So this one especially, I would say change this to a percent, because that would be annoying to have to simplify. And I can't really picture what this is. I'm guessing it's going to be around like 60%, 70% maybe, because I'm just kind of looking at the relationship, honestly, between like 9 and 13. But let's see what this actually ends up being. 68, and then that 7 is going to bump that 9 up, and when that happens, we actually do round to the whole number. So this is going to be about 69%, because you'd have to round this out pretty far in order for that to not bump up, because that bumps that, and so when you're looking at the 9, you bump up to the next whole number. Okay. All right, a couple more examples, and then that'll be it for this first lesson. Okay, so this is calculate the following using theoretical probability. So again, in theory, what should happen? So if you roll a dice 36 times, how many times would you expect to roll the number 5? Well, again, in theory, it says that if we were to roll the number 5, there is a 1 in 6 chance that that's going to happen. So if I want to know what that would translate to in terms of 36 rolls, I could set up like a little proportion here. So here's my theoretical probability that should transfer over into the experimental probability. So when we cross multiply, we would get 6x equals 36. So we would expect to roll a 5 6 times. Now for some of these, you might just be able to do this like conceptually without showing the work, and that's fine. So this next problem says, if you picked a card from a full deck 2,500 times, how many times would you expect to pick a king? Okay, so there are 52 cards in a deck. Okay, 4 of those are kings. So 4 out of 52 would be my theoretical probability. So in theory, 4 out of 52. And so I want to translate that to 2,500 picks. That ratio should be the same. And you can simplify that fraction first if you want to. So when I cross multiply here, I would get 52x equals, and then 2,500 times 4 would be 10,000. And then when you take 10,000, divide it by 52, you get about 192. So I'm going to round down here. And I would probably still encourage you to round down even if that were bigger than 5. Just kind of like when you're rounding like home, like people, living object type things, we usually round down. All right, so next question says, if you picked a card from a full deck, so again, that means that there are 52 outcomes, how many times did you expect to pick a heart? Okay, well, there are 4 suits. Each of them is going to have the same number of cards, so if I have 52 total cards, and I divide that by the 4 suits, that means there are 13 of each suit. 13 hearts, 13 spades, 13 diamonds, and 13 clubs. So that same ratio should be translated to 100 picks. So that would be 52x equals 1,300. 1,300 divided by 52 is 25. So I should pick a heart 25 times. Okay. Last problem. It says you have a bag that contains $5 in quarters, $2 in dimes, and 75 cents in nickels. What is the probability? Now this one is saying as a percent that when randomly selecting one coin out of the bag, it will be a quarter. Okay, so my probability should be the number of quarters, that would be my favorable outcome, over the total number of coins. Okay, I know neither of these things. So we need to first figure out how many quarters we have. Well, if we have $5 worth, and there's 4 quarters in $1, 4 times 5 is 20. So 20 quarters. Okay, so if we have $2 in dimes, there's 10 dimes in $1. 10 times 2 is 20. And if we have 75 cents in nickels, 75 nickels worth 5 cents. So that means we have 15 nickels. And so that means I have a total of 55 coins. So 20 out of 55. As a percent, that would be about 36.4%. Okay. All right, so let's see, not tomorrow. Tuesday and Wednesday of next week, we will do 2 more lessons, and then Thursday, which is crazy already, the last day of the school year, you guys will have a quiz. So your assignment after Wednesday will be like a review assignment over everything, and then I'll give you a little bit more practice if you want it, and then we'll end with a quiz. All right, let me know if you guys have any questions. Homework is on Canvas.